All right, hello everyone. I'd like to take just a few minutes to finish up our discussion of fluids, and that should help you a little bit with the homework that I know you have to do. Before I go to the next slide, I did want to say just a little bit more about Bernoulli's equation with a negligible height difference. Keep in mind we're dealing with a case here where the 2 points in the fluid have a difference in height relative to some y equals 0 that's just not a whole lot. So like in the case of the airplane wing, the difference between the top and the bottom of the wing, those 2 points in the fluid, is not a tremendous amount. So we have a situation where if I have an increased velocity, I end up with a decreased pressure. And don't forget, this is a perpendicular pressure to any surfaces that are in that fluid. Another example of this that I could give is when dealing with tornadoes. Tornadoes. You might have heard that in a tornado it is recommended that you open your windows, which seems a bit counterintuitive because the windows, there's going to be a lot of wind, all your stuff's going to get blown around everywhere. But it turns out that the reason for this is because of trying to avoid the pressure differential that can occur because of the high velocities on the outside. So if you might imagine, let's just deal with like a really simple sort of house. And we imagine there's a tornado. Whee! Scary tornado. There's a lot of wind that's blowing past this house. And it turns out that, roughly speaking, maybe the velocity of the air is 0 on the inside if the windows are closed, but on the outside, the velocity is high. Well, if that's the case, then if I look at the pressure on the inside upwards and the pressure on the outside downwards, there is a difference. We have low pressure on the outside and higher pressure on the inside. That pressure differential can be enough to take a roof off a house, or if the house isn't firmly grounded, maybe even lift the house or tip it over. And if you're thinking how much of an effect could that have, just sort of using some average sort of numbers for a tornado and just a rough size for a house, the pressure differential could be on the order of about 800 pascals, which again, you might be thinking, well, that's not a whole lot compared to, say, atmospheric pressure. But keep in mind that pressure is being distributed over quite a large area. So maybe if we were to look at the force, which is the pressure times the area of that roof, in that particular case, this could end up something maybe on the order of 27,000 pounds. That's a lot of weight. You might think of it as pushing upwards on the roof, trying to lift that off. So the key is open a window. If I open a window here on the side, then that air can flow in, and if I open on the other side, it can flow out the other way. And then we don't have a pressure differential, we just have high winds everywhere, which is bad for the stuff, but better for the house. So let's back those up, and everything is there. So that's Bernoulli's equation with a negligible height difference. What if we change things a little bit, and this time deal with a negligible velocity difference? On the other hand, maybe we do have a difference in height. Maybe we have a fluid that's flowing through a tube. Let me turn that off. There we go. Maybe we have something that's flowing through a tube, and the tube's diameter never really changes, but it goes up to a new height, and yeah, the drawing's going to be terrible as always, but maybe it stays roughly the same size the whole way, such that I don't have a decrease or an increase in cross-sectional area, which would lead to a change in the velocity. So let's just say that maybe here at the bottom, this is y equals 0. And let's call this lower point 0.1 and the upper point 0.2. And let's say that things are sort of flowing like this. Well, if I now look at Bernoulli's equation, so P1 plus 1/2 rho V1 squared plus rho G Y1 equals the same thing. Well, in this particular case, you can imagine that my y1 is 0, so that term is gone. y2 is going to exist, but these two velocities are the same because I don't have a velocity difference, so they cancel each other out, which leads me to P1 equals P2 plus rho g y2, which should look pretty familiar, right? This is just our equation that we had for a difference in pressure as I go deeper inside a fluid. Point 1 is at a lower level in the fluid, so it has additional pressure. So let's take a look at some examples. First of all, let's say that we had some sort of large vat of fluid like this, and this is open at the top. We'll say it's open to atmosphere. And here we go, big cylinder of fluid. There we go, something like that. Whoops. Okay. And let's say there is some level of fluid in here that's maybe right there. Okay. So, first of all, a key thing when dealing with fluids in the situation is that, we'll say that points in the fluid in contact with the atmosphere are at atmospheric pressure. Think about it just a little bit. If I look at this particular surface and imagine just water molecules or whatever fluid we have right there at the top, and imagine that there's a atmospheric pressure pushing down. Well, if the water level is staying at that location, well, I don't have a net pressure, which means there must be an equal pressure that's pushing up at that point to keep the water level from going down or up. It can't have greater than atmospheric pressure, otherwise it would be going up, pushing against the atmosphere. And it can't have less, otherwise the water level would be going down. They have to be equal at that point. So let's say, first of all, if I were to just maybe go down to this level, if I wanted to know the pressure at that location, I could say that we have number 1 at the top and number 2 is down at this particular depth. Well, in that particular case, P2 is going to be equal to P1 plus rho g. We could call this Y1 if we wanted to. So let's see, Y1 is just going to be the depth of the fluid at that particular point. So this is going to be Y1. And then we have our pressure that comes from the pressure at the top, which is atmospheric pressure, plus this other term that comes from a depth of the fluid. So this is exactly like what we had before. No difference there at all. So what happens if I change this and instead put a hole at that location? You can imagine before I put the hole in the cylinder, there is pressure here pushing against the wall, and it wants to come out. The fluid would like to be released. So let's see, let's move this over to the side, and we will say that this is what you get if there is no hole. That's the pressure on the side of the container at that point, the pressure at all points in the fluid at that particular level. But let's go back over here now and just put a hole right there in the side. We'll say that the hole doesn't really have a lot of height, but its center is sort of right there at the middle. You can imagine that fluid is going to come gushing out, and it will be sort of a projectile of fluid, if you want to think about it that way. So let's see what happens now if I have a hole. So with a hole, we could use Bernoulli's equation. V1 plus 1/2 rho V1 squared plus rho g y1 equals P2 plus 1/2 rho V2 squared plus rho g y2. So let's set the bottom location as our y equals 0, which means that term is going to be 0. You might imagine that at the top, assuming that the hole is much, much smaller than the diameter of the vat, this velocity is very small. In fact, it's so small, I'm going to just set that equal to 0. Also, P1 and P2 are both in contact with the atmosphere, so they must be equal to atmospheric pressure. Think about what happened. P2 was at a high pressure because of the depth. I've relieved that pressure by popping the hole in the side of the cylinder, which now has dropped the pressure at location 2 to match atmospheric pressure. If that bothers you just a little bit, you could say zoom in, like right here, and imagine this tube of water that's coming out. It comes out perfectly horizontal. It doesn't go up this way, which means it doesn't have a higher pressure than atmospheric pressure, and it doesn't just like go straight down. It's not less than atmospheric pressure. It comes out perfectly horizontal. So it's equal to atmospheric pressure at that particular point. So that means that these two terms, P1 and P2, are equal and cancel each other out. So now I just have rho g y1 equals 1/2 rho v2 squared. So let's see, the densities are in both, so they're going to cancel each other out. And I can solve that for the velocity that the fluid escapes the cylinder, and it's going to be the square root of 2gy1. And that should look terribly familiar because we had very, very similar results when we dealt with, say, objects that were falling a certain height from conservation of energy. That would be the velocity at the bottom if an object fell in free fall from height y1. So we get a very, very similar result. Here's something that you could think about that would be very, very interesting. If we were to, on top of this, maybe, I don't know, make a little attachment. Let me draw another cylinder over here to the side. Oh, there we go. There we go. Terrible cylinder. Again, we're going to put a little hole in the side. There's a water level that's here. And let's say I were able to sort of immediately redirect the water so that it went up. So it shot up this way. How high do you think it's going to go? Well, it's going to go exactly as high as what I'm showing there. Assuming no air resistance, no losses due to non-conservative forces, of which of course there are going to be some, we could say that, well, it's going to have enough velocity to go back up to the original height. So you can imagine it shooting right back up to this water level, and then as more and more water comes out, the water level is going to fall, and how high that goes in the air is going to fall. So there's enough pressure from the water here to launch the water up to the height that that pressure starts from. So that's our first example. Doing another one. Let's see. Here we have a horizontal section of pipe. Water's flowing through it at a certain pressure, and they give us the cross-sectional area. It then contains a section that moves downward a distance and connects to another horizontal pipe with a different cross-sectional area. So we could draw a diagram for this, and let's see, which one is bigger? The top one is bigger, so we could say that maybe at the top it looks like this, and then goes down, and then I'm going to say that at the bottom it is smaller, so it looks something like that. So from the top of this down to the bottom is 2.3 meters. They also gave me the velocity at the top, and we're going to call this location 1 and the bottom one location 2. So V1, it said, is 30 centimeters per second. They also gave me the pressure at point 1, which is 2.3 times 10 to the 5th pascals. And finally, the cross-sectional area at point 1, which is 5.3 centimeters squared. Down at the bottom, I get area 2, but that is it, 2.5 centimeters squared. So a few things that we can find. First of all, what is the speed of water flowing in the lower section of the pipe? Speed of water flowing in the lower section of the pipe. So for this, since I have the two areas and I have one velocity for part A, we can simply use the continuity equation and solve that for V2, so it'll be A1 V1 over A2. And notice everything here is in centimeters, centimeters squared, and centimeters per second. So we'll keep that such that things cancel out and give me centimeters per second once again, and you should get 64 centimeters per second for that. For part B, we can switch over to Bernoulli's equation. So let's write that out. And let's see, let's say that this bottom level is going to be our y equals 0, which will make y2 equal to 0. And notice it's asking me to find the pressure of the water in the lower section. So it's just a matter of rearranging this equation, pulling this term over to the other side, subtracting, and then you have everything you need to solve for it. Let's see, we have the pressure at the top, we have the velocity at the top, we know the height is 2.3, and now we know the velocity at the bottom, so you can solve that for pressure 2, and you would get 2.5 times 10 to the 5th pascals without me rewriting Bernoulli's equation all over again. And then finally, one additional example here. Let's see, we have a cylindrical bucket open at the top, so atmospheric pressure at the top. They were given the diameter and the height. The circular hole with cross-sectional area given is cut in the center of the bottom of the bucket. Water flows into the bucket from a tube above it at a given rate, so we have a volume flow rate. So you can imagine the water's coming in, but also due to the hole, it's going out. At some point, things are going to balance such that the water level is no longer rising. So it would fill to a certain point, and then the rate in and the rate out equilibrate, and the water doesn't go any higher. So, a quick diagram. Let's see. Cylindrical bucket, something like that. And that is not good at the bottom. Let me try that again. Still not good, but you get the idea. And there's a little hole there in the bottom. So let's see, so there's fluid that's going in at the top, and then there's going to be fluid that's coming out of the bottom. Okay, so let's see, the flow into the top is the volume flow rate. So if you want to think of that as A1 V1, for the top is 2.25 times 10 to the minus 4 meters cubed per second. And let's see, what else do we have here? We know the diameter at the top. So this diameter all the way across is 15 centimeters. And then this little diameter at the bottom, nope, they gave us the area. So A2 is 1.53 centimeters squared. And we want to find the height of the water. So first of all, let's see if we can find something about the velocity at the bottom. So we can use, again, the continuity equation. And yeah, there's a random level in here somewhere at some point that's going to stabilize. We don't know what that is, though. So point 1 here is at the top, point 2 is the hole at the bottom. So A1 V1 is equal to A2 V2, and we know that A1 V1 is this entire thing, so I can solve for V2, which is going to be 2.25 times 10 to the minus 4, divided by area 2, which is, I'll be a little careful here, that's in centimeters squared, so you'll have to do a conversion there. And that's going to be 0.000153 once we convert that to meters cubed, or meters squared rather. So let's see, that's going to give me a new velocity of 1.47 meters per second flowing out the bottom. And let's see, my notes have problems over here. What is wrong with the notes? There we go. So once we have that, we can use Bernoulli's equation. So P1 plus 1/2 rho V1 squared plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho G Y2. And a few different things that we can do. First of all, once it's stabilized and the water level is no longer rising, that velocity at the top is now 0. So that one is gone. What else can we say? Both 1 and 2 are open to atmosphere. So they are going to cancel out. So V1 is equal to 0. We'll say when water stops rising. And P1 equals P2 equals P atmosphere. So that's how we can get started. Let's see, what else do we have here? We could also say that at the bottom, we could let that be y equals 0. So let's put that in over here. So that last term cancels out. And then I just have rho g y1, and y1 is what we're looking for, is equal to 1/2 rho v2 squared. The densities cancel out, and life is pretty happy. You can solve that for y1, and you should get 0.11 meters. So hopefully you can start to see the approach of mixing the continuity equation and Bernoulli's equation and how some of these problems can be approached. Which brings us to the remaining part of the chapter. Water flows through a 1 centimeter diameter pipe and is connected to a 1/2 centimeter diameter pipe. Compare the speeds in these two. So you could use the continuity equation for that. And keep in mind that the area in both of these cases is going to be pi r squared if we're assuming a circular cross section for the pipe. So in that particular case, if I have the diameter, I'm also having the radius, and that gets squared. So that means I have r over 2, which is getting squared, which is r squared over 4. So the area is getting cut by 1/4. And, well, if the area gets cut by 1/4, then the velocity has to be 4 times larger. Let's see. In this particular case, you will notice that the cross-sectional area here is decreasing. So if the cross-sectional area decreases, then the velocity has to increase. And if the velocity increases, then we know that the pressure decreases. Now, I don't know whether this particular blood pressure is the same as the one that we hear about medically, but if we're just talking about the pressure of the blood perpendicular to the walls of this artery, then in that particular case, if it speeds up because the area is restricted, you can use the continuity equation to say the velocity goes up. So A1 V1 equals A2 V2. So the area goes down, velocity must go up. And then Bernoulli's equation, where the negligible height difference is say that as the velocity goes up, then the pressure goes down. And then finally, a similar idea, how's the smoke drawn up a chimney affected when there's a wind blowing outside? If the wind is blowing outside, then the pressure decreases. And if the pressure decreases, then it's easier for the smoke to get out of the chimney. And that is the end of our fluids chapter. If you have questions, please don't hesitate to email me, especially as you're working on homework. The next chapter will be coming, but it's probably going to be sometime on Wednesday before I get that posted. Thank you for listening/watching, and I hope you have a good holiday break.